Well, hello everyone. Welcome to this Tech Talk. We'll give it another 1 minute or two before everyone joins. Yeah, for anyone who joined in last 30 seconds, we are about to start. We'll start in another 30 seconds or so. Okay. Hi everyone, and welcome to this Tech Talk series on generative AI for security. And since the rise of ChatGPT, almost everyone wants to know what values can ChatGPT add to their product. In our case, we focus in the area of cybersecurity, along with the broader area known as generative AI. I'm Abhinav Mishra, and I have been with Splunk over 4 years, and my area of expertise is machine learning. With me, I have Kumar Sharad, who is an expert in
Everyone.
security and privacy. So here's a general outline. Initially, we present some simple out-of-box use cases with ChatGPT. We also look at the opportunities and challenges associated with it. We then go over the use case of phishing and how can we solve it with autoencoders, which is a technique within a realm of generative AI. Later, we look at fine-tuning large language model, and we look at the use case of DGA, also known as domain generation algorithms. And here we will learn how we can use large language models to detect them. Later on, we look at another technique known as generative adversarial network and how we can utilize it to generate synthetic but realistic data for the domain of cybersecurity. As a motivating example, I asked ChatGPT, hey, give me a SPL for DGA detection. And again, DGA is domain generation algorithm, and these techniques are used to exfiltrate data from your machine to an outside server. And we can look at a very simple SPL generated by ChatGPT. It is looking at the length of the domain, it's counting the number of unique characters, and based on that, it is telling us whether a domain is a DGA or not. But I have worked in the area of detecting DGAs, and I know that this particular detection is at least 20-year old, and it won't work in current landscape. So what do I do next? I asked ChatGPT to give me a much more advanced SPL. And this time I can see that, it's filtering something from Alexa top 1 million domains. It is coming up with more interesting regular expressions. It's also looking at entropy. I mean, from my experience, I know that this is not a state of the art detection, but still it gives a much better detection compared to what I asked earlier. So this raises a few important questions. Why didn't the Chat GPT give me this particular SPL at the first place? How do I know that this particular SPL is the state of the art? And can I actually trust this detection? And all these questions, one can think of them under the umbrella of hallucination. What it means is a large language model such as ChatGPT could be hallucinating when the model starts to make up things. So the takeaway is use ChatGPT to write your own detection, generate SPL or anything with a grain of salt. Ensure that whatever is coming out of ChatGPT is fully functional, it works, and have some parallel baselines with which you can compare against. And generative AI is beyond ChatGPT. It could be used to generate images. It could be used to generate audios. Very recently, I learned a startup obtained a funding of 80 to 90 million dollars, and all it's doing is generating audio dubbing into different languages. And this could be used by Hollywood studios if they have a movie. Can they generate a very realistic looking dub into other languages? Before we dive into generative AI techniques, let's cover some basics. In this example, we are training a neural network that classifies an image as a Spider-Man or not. The way it works is first we convert this image into a feature vector. In case of images, it is three matrices containing RGB channel information. For simplicity, let's assume that it looks like a matrix containing certain values. Then we present a lot of example images to this particular neural network. And example contain both Spider-Man and non-Spider-Man images. Then the neural network learns weight and update its weights. We call this phase as training. Once the training is complete, the neural network will be able to classify an image as a Spider-Man or non-Spider-Man. So now we move on to a different kind of neural network known as autoencoders. And in this particular example, we are looking at denoising autoencoders. So this particular neural network, it is simply removing noise and making the images sharper. And this particular neural network has two components, encoder and decoder. And we call it autoencoders. All the large language models, including ChatGPT at some level, use some combination of either decoder, encoder, or both. Autoencoder learn how to recreate the information given initially, even if the information is noisy. It initially maps the information into a low dimensional vector and then try to recreate the information using decoder part. For example, in these bunch of noisy images, encoder initially convert all these noisy images into a low dimensional vector, which is shown as compressed representation here. And then we have another component known as decoder. It converts it back into noiseless images. Google Photos is a very good example of this particular architecture where they convert your images into this compressed representation on cloud. And on your cell phone, all they send is that compressed representation, and the decoder component converts it back to the original image. Now we have a good understanding of autoencoders, but before we go into the use case of how do we solve phishing, let's go over the problem of phishing. The screenshot on the right-hand side shows a login screen which resembles Google login screen. It is visually similar to Google login, but pixel-wise, it is different. What it means is the most image matching algorithm will tell you that this is not a Google login page. However, to a user, it would appear as a Google login page. And on the top URL, we can see it is coming from some random URL. Sometimes it looks legitimate, sometimes it is not. And the idea of phishing is tricking users into entering their actual credentials so that they can later exploit it. So how do we use autoencoders to detect phishing? Again, going back to previous example, we know that visually it looks like a Google login, but pixel-wise it is not. So what we can do with autoencoders is we can send a lot of example of phishing Google pages. We can create them artificially, or we can obtain the realistic example and then train them and map it back to the original Google login page. So whenever there is a visually similar looking Google page, we will know that it is actually a Google page. Likewise, we can create a lot of example for different type of logging, like PayPal, Facebook, Microsoft, and whenever those login phishing examples are presented, they will be mapped back to their original class. And so this is one way we can use generative AI for phishing. Now I hand it over to Sharad to go over more use cases and techniques.
Thanks, Abhinav. I'll be broadly talking about two topics. One of them is large language models, and the other one is generative adversarial networks and how these are used to help out with security use cases. So Abhinav talked about encoders and decoders, and these are very important components which go in together to create transformers, which is the basis of most modern large language models. Now, the ChatGPT application or other chat-like applications which have gained popularity over the past year or so are basically a thin veneer over top of these large language models. These are the powerful engines which eventually power all these applications. These particular kind of models fall under the category of what is known as generative models, and which is different from traditionally known discriminative models. We will spend some time, we will look at it, what the difference between the two kinds of models is in the next slide, but it is important to note that these are different approaches. And what's important with generative models, or what the advantage that they provide, is that they can be converted to behave discriminatively. And this allows us to use LLM, which has been trained for a specific application. So let's say just human-like chat, where you can talk to it, ask about the weather in London in July, or perhaps which days are government holidays in a particular country, and so on. You can take the same language understanding and convert it to ask questions like, is this particular sample malicious or benign? Now, this sample could mean anything, but this depends upon the use case. So fine-tuning is the process where you use a base LLM and convert it into answering questions that you are interested in. And we can use this process to repurpose LLMs to our use case. So let's take a look into what does discriminative versus generative models mean. So let's say we have a data set where A represents the data label and B the feature vectors. So data labels could be either binary or multiple, and the feature vector is basically a representation of your data sample, where in case of an image, it could be pixels and intensities and so on. A discriminative model tries to estimate the probability of the data label given the feature vector. So given the picture, if it belongs to a cat or a dog or a house and so on. Whereas a generative model tries to learn the joint probability distribution of a label and the feature vector. So it tries to learn what is the probability that this kind of feature vector appears along with the label of a dog, for instance. And using Bayes' rule, we can convert a generative model to a discriminative one. Now, there are various ways to fine-tune a model. I'm covering some basic ones, and each one of them progressively gets more expensive. So let's see what they are. So you start with the label training data set, and you feed it to your LLM, which is basically a pre-trained transformer. And you take the output of that, which is essentially a bunch of numbers, and you use that as a feature vector to train another classifier. And this can, and during training, you only update the parameters of the classifiers and everything else remains frozen. Additionally, what you can do during classification is also add other connected layers, which form a part of the pre-trained transformer or the LLM. And then during the training phase, you just update these connected layers and finally output a class. And finally, you can get even more involved where you not only update these connected layer parameters, but also the parameters of the pre-trained transformer. And each one of them is progressively more expensive than the last one. But this also gives you a performance boost in most cases. Now let's look at a use case to extract this or harness this power. As Abhinav mentioned in his section, what DGAs are, they are basically domain-generated algorithms. These are used to generate domains which could be, which are mostly used for malicious purposes. And it's easy for an adversary to use an algorithmically generated one, as they could just set it and forget it. Most of the times, these are random looking domain names, or they have some pattern to it. So there's a whole bunch of families which do this. And if we can curate a data set of these DGAs, and then we have a benign set of URLs or domain names, then we can fine-tune an LLM to tell us which one is which. And this gives us substantially better results compared to traditional approaches. And this approach not only comes at a very limited changes to the LLM, but also provides us with quite a few benefits. This allows us to amortize the work that we spend on creating the model and the architecture, as we can point it towards another task, which is different but similar, as in the text-based. Then we can detect other malicious activities for that data set. So here's an example of a curated DGA data sets. You can see that these random looking domains are malicious as compared to the benign ones. And once you tell the LLM, this is what we are looking for, it can do a pretty good job. Another use case is typo squatting, or detecting typo squatting using LLMs. So typo squatting is a form of URL hijacking, where you type a URL and you're led to a website which you did not intend to visit. For instance, for Splunk.com, if you reorder the characters by mistake or there's a typo, then adversaries may have hijacked that particular typo, and then you are led to a different domain. And then you could also be asked to provide credentials or credit card information, perhaps not in the case of Splunk, but imagine a bank website or things like that. So this is also a use case which suits very well to the LLMs, where you can fine-tune an LLM to detect typo squatting. And additionally, what more you can do is you don't have to directly use the output of the LLM as a final result. These can be combined with other signals, such as the time during which these websites are visited, how long the connection lasts, and so on. There's a bunch of things which you can add on top of what you get out of the LLM to create an even more robust and a better performing model. So this is a list of typo squats of possible typo squats of Splunk.com. You see that there's either letters inserted or numbers inserted, or dots missing, or letters reordered, and so on. Let's do a visual recap of what we learned so far. So originally, applications like ChatGPT have been used to answer questions. So in this case, a simple question, is Christmas celebrated in October? And very well answers no. However, after we fine-tune it, we can ask a different question. For example, does this cryptic-looking URL represent a DGA domain? And in this case, answer is yes. Similarly, you can ask it another question, like, does this strange-looking website a typo squatting? And again, the answer is yes. But the usage of LLMs doesn't stop here. They can also be used to generate data. So this is a simple example where we try to generate a two-dimensional data set. So basically, it has only 2 points, and it has quite a bit of intricate patterns. So this data is not distributed simply. And yet LLMs do a pretty good job at mimicking this. And this leads to us to the next section of our talk, which is generating data using GANs. So GANs have been popular because of the great performance in generating very human-looking like images. So they are like a type of a neural network that learn and replicate distribution of training data. And it consists of two main components, the generator and the discriminator. So here's a look at a simple GAN architecture where you see that the generator, so the main goal of the generator is to come up with images, or in this case, images which look like real images. For instance, let's say we are looking at images of dogs. And the generator wants to create a synthetic image which looks very close to that of a dog. So it may start with something of some kind of a sketch. And then over several iterations, it improves its output. The way it works is both generator and the discriminator, they're both neural networks which are handed two tasks, one task each rather. So generator's task is to come up with an image which looks as close to real as possible, whereas the discriminator's task is to differentiate between a real image and the one which has been generated synthetically. And during several iterations, it tries to figure this out. At some point, one of these model wins. It's a zero-sum game, so both cannot be successful. And eventually, a discriminator would not be able to pick real images from those generated synthetically, and it will give you a response as good as a coin flip. And in that case, you know that there is no useful input that could be used by generator to improve its performance. How the discriminator performs is critical for a generator to improve or update its parameters and come up with an even better looking image. So let's look at an example. So this image of this person has been taken from the website called This Person Does Not Exist. And quite true to its name, it doesn't exist. It has been generated synthetically. And I would argue that this person looks very close to somebody that could actually exist. However, if you look a little bit closely, you see that GANs, despite being very, very good, leave some artifacts. So this image looks digitally touched for some reason. And you know, there have been techniques which have been developed in the past 6 months or so, which do even better job. But yeah, we are getting really close to what could be considered human or not. So these GANs are not just good for generating very high quality images, but they can also be used to generate tabular data, which is the most common kind of data that we find in security applications. Think of Windows logs or network logs and so on. And additionally, in security cases, what happens is many times customers are worried about privacy of the data sets, which is to say, if we have a data set and it is handed over and then we train models on it, what does the model learn that could lead back to the customer's data that has been shared with us? So there are techniques which allow us to train a model in a private manner, which is to say that we can add carefully calibrated noise to our training, which guarantees that the privacy of the data is maintained. We can use techniques such as differential privacy to train using private gradient descent methods. What the differential privacy guarantees is the following. Imagine a world in which there is a person present in the data set and another world in which the person is not present in the data set. And the adversary is not able to determine which world they are present in given the output of the data. So based on the computations on the data that you make, the adversary is not able to tell, and this is guaranteed through mathematical means, that whether a person is present in the data set or not. And this is a very, very strong guarantee that could be provided. Using techniques like these are extremely valuable to come up with models for which privacy and sensitivity of data is important. Also, if you don't have enough data, GANs can help you generate more of it. And this is also an important. This is also important in training models for which data is sparse, as in many security use cases. Let's say false login attempts, they tend to be very highly skewed. So there would be far more successful attempts as compared to malicious ones. GANs can handle very complex data structures, and they could also learn the structure of the data in the sense that often you have columns of data related to each other, and GANs can mimic this very well. And once you have a model trained, you don't need the data anymore. So GANs provide a way to not only generate tabular data, but also textual data. So these are some DGA domains which have been generated using GANs. Although it may be hard to tell with such a small sample size, these look far more realistic as compared to completely random looking names. And once we generate domain names like these, we can use them to train our models. So this gives us another benefit. So this brings us to the end of the technical section of the talk. Before we head on to question and answers, I would like to point you to several resources. So do take a look at the community hours related to generative AI, which is upcoming in the next few weeks. We will be taking questions and just offering solutions to any questions that you may have. Do take a look at our Splunk blog as well. It has a number of articles which covers the work that we have been doing. Of course, all this information will be shared with you in an email after the talk, which will also contain the recording of the talk. Finally, you also head on to the community.splunk.com, where you find interesting question answers, discussions, and ideas, and so on. All right, that brings us to the end of the talk, and we are happy to take any questions that you may have.
Thanks, everyone. So there are some questions asked by audience. So let me repeat those questions. First question is, what are the privacy considerations when using generative AI models for security use cases? Do you want to take a stab at this, Sharad?
Yeah, sure. So as we covered, there are techniques which could be used to offer strong privacy guarantees while training machine learning models. And these techniques guarantee mathematically that your data is not going to be used in a malicious manner. So this also guarantees that no matter if your data is part of the training data set or not, the adversary or the malicious party learns the same information if it was a part of the data set. So privacy-wise, techniques are always evolving. Of course, there's a trade-off. When you do such things, you have to spend more computational effort, as well as take a little bit of a performance hit, but these things are always improving.
Another way to look at it is, nowadays there is a discussion, like a lot of these largest language models, are they good at memorization? What it means is, if you present your training data, are they learning something from it, or they are just memorizing? Because in case they are memorizing, they will retrieve exactly what was presented to them. And if there is any private information, they might reveal it. For example, if there is a lot of credit card data on which LLMs are trained, and I ask the question, hey, can you give me certain credit card numbers with their dates which can work today? If they have memorized, they will give you the answer, which violates privacy. Second question
Okay,
is, yeah, go on, Sharad.
yeah, I was just going to read the second question. How significant of an accuracy improvement is achieved with fine-tuned LLMs as compared to traditional approaches? You want to go ahead, Abhinav?
So I would say, like, before using LLM, we need to have certain baselines. We should also already have methods that establish, okay, this is the best we can do with our simple machine learning models. And then we can start fine tuning our LLMs and see, like, whether it works in practice or not. And there are certain situations where it is guaranteed that LLMs will give you better answer. For example, if there are situations where your use case relies on any kind of language, for example, email phishing or DGAs, or something is a spam or not, or we are looking at images, large language models, they have a very good understanding of intrinsic relationship within language, and they can provide better answers.
One point I would also like to add is that although in the final, let's say, accuracy percentage or whatever metric you are using, the increase may be minuscule. What is most notable is that there could be certain classes of your data where your model doesn't perform well. And in our experiments, we have seen that the result of in these hard cases is specifically much, much better as compared to your baseline traditional model. So although the overall improvement might be minuscule or small, if you break down where the changes are happening, you will find that certain hard cases have become a lot more easy.
One question is, beyond DGA and misinformation, can you think of any uses of generative AI by adversaries? So, I mean, LLM, large language models, they are just a tool. They are going to work whether they are in hands of, people who are ensuring security or adversaries. Then it becomes more like a cat and mouse game. For example, we train large language model to detect something. And if adversaries learn that, okay, large language model can detect these particular things, they can train their own large language models and tell them, hey, give me examples which are not like these, and that should go undetected. So it's kind of a loop. Like, adversaries, they generate some example, we find out those examples, then adversaries learned, okay, these examples, they don't work, they need to generate something else. So in the end, it's like a cat and mouse game.
One point I would also like to add is that when you are defending against an adversary, it's very important to consider which kind of adversary you are defending against. So normally when you lock your door, you lock it for perhaps the average burglar. If somebody turns up at your door with a shotgun, perhaps it wouldn't work. So you need to figure out which kind of adversaries you want to protect against. Not every adversary can go around spinning LLMs and generative AI machinery and attack you. This is a very, very sophisticated class of adversaries, which means that you have, by using these techniques, you have already removed a very large number of adversaries.
Next question is, are you using ChatGPT free or the version? So until a month ago, I was using free ChatGPT known as 3.5, and very recently I moved to ChatGPT 4, which is a paid version. For generating DGA SPL query, I used GPT-4, but again, like I had to ask ChatGPT, can you give me much more advanced answer? And I'm not even sure whether the answer ChatGPT 4 gave me, whether it works or not. For example, there is another related question. Isn't DC a stat function, not an eval function? So we have to ensure whatever ChatGPT outputs, it may look realistic, but it should work in practice. And if we go into asking large language model, perform a chain of thought, then usually it gives a much better answer. What it means is, we give it a series of prompts and it forces ChatGPT to come up with a much better and precise answer.
Okay, there's a question, probably not ML related, but is there a way/site to differentiate photos created on sites like this person does not exist from real ones? So this is essentially a cat and mouse game. So there were some conversations going around that kids have been copying homework and writing essays using LLMs. And then there was this research which claimed that they can detect LLMs created text from non-LLM created text. The problem with such approaches is once the adversary becomes aware of the defense, they could go right back and say, okay, I will acknowledge the fact that whatever defense or whatever filter you have to separate LLMs versus non-LLM text, and I will make it part of the training. And they will generate new set of new data set or a new image or a new essay. So the takeaway message here is an adaptive adversary is a moving target, and it's very difficult to protect against them. So I'm not sure if there are any tools which are conclusive in that field.
I mean, my take is in theory, it is impossible. For example, let's say at this time, if I have a lot of examples which are machine generated images and a lot of real images, I can always train my machine learning classifier to classify these two into two different classes. And it will work now. But tomorrow, adversaries, if they collect these examples, they know like where exactly how classifier works, they can come up with more examples. And simply by using generative adversarial networks where classifier is forced to provide examples which are as good as what we have now. So today we can have answer, but tomorrow again, it's a cat and mouse game. We have to update our models as well so that we stay ahead of adversaries.
Okay, next question. Can you give some practical examples of generative models applied over data in the security field, or maybe a reference/link to such examples and use cases? So just to jog your memory, we covered 3 practical examples. So one was covered by Abhinav, which used decoders and encoders to figure out phishing related web pages. And 3 others are covered by me. One was typo squatting, one was DGA, as well as generating data to train a model privately. So these are very practical applications and most commonly used in security field.
I will say email spam filter, like wherever there is an element of languages, LLMs, they are going to win. And for other use cases, we may have to think beyond large language models. We may have to fine tune our own models, or we may have to use like auto encoders, which doesn't come out of ChatGPT.
So how? Yeah, go ahead, Abhinav.
Okay. So next question is, what are the cost considerations while deploying large language models? So large language models, typically we need to have GPUs available to us simply because running them on CPUs is non-trivial. There are ways we can run them on CPUs if we convert those models into Onyx, but in general, GPUs are preferred simply because you get like 100 times performance. And second thing is, like every single query we send it to a large language model, it is going to cost. If we have a really fast GPU, maybe we can answer 10,000 queries, versus if we have a simple logistic regression, it can give us 1 million queries per hour. So again, like there is a big performance drop when we start using LLMs, and the cost, it increases significantly. And with large language models, we again need a complete different ecosystem compared to simple ML ops. For example, if LLMs give me an output, there is no guarantee that it's not making stuff up. How do we validate that? So that is where we need some kind of human supervision as well.
So again, this brings us to the point where any adversary cannot just pick up one of the generative AI tools and start attacking people at scale. This just does not work. This has to be a sophisticated adversary. Yeah, so that kind of brings us to the end of mostly questions. Is there anything else we should cover, Abhinav, or are we good?
I think like if there are, yeah, we are going to share all these resources in an email, and there will be an upcoming community hours. So if you have any questions around our talk or any other ideas, or if you want to know how you can have generative AI within your organization, please come to our community hours.
Yeah.
Thank you, everyone, and
All
have a
right.
really
Thanks, everyone, and thanks for your attention. Bye.